All right, ladies and gentlemen, welcome back. So today we're going to pick up talking about our next class of macromolecules, and these are lipids. So this family of compounds technically isn't a true macromolecule in the sense that it doesn't have a true monomer-polymer structure like the rest of the macromolecules that we're talking about do. Um, so they're going to have component building pieces, but it's not going to look like a monosaccharide to a polysaccharide or an amino acid to a protein. So this class of compounds includes both your fats, your phospholipids, and your steroids. And the big thing that really connects all of these compounds in this category is the fact that they're insoluble in water. So they're hydrophobic molecules. They don't like to interact with water, so they don't really dissolve well in them either. Mostly because they consist mainly of hydrocarbons, which if you remember back from our discussion about organic chemistry, hydrocarbons are just big chains of carbons and hydrogens, and they are nonpolar. So since water is polar, remember like dissolves like, so polar to polar, polar to ionic because they all have charges, and then anything that it has a charge, like a polar or ionic compound, won't really interact with something that's nonpolar because nonpolar compounds don't have charges. That being said, polar to polar, those would dissolve in each other. So I could get butter to dissolve in oil, but you're not going to get oil to dissolve in water. So when we look at fats, this is probably the category that you're most familiar with within this family of compounds. And fats are also known as triglycerides or a triglycerol molecule. And that's because they consist of two smaller pieces that are formed by a dehydration synthesis reaction, and that is your glycerol and your fatty acids. So a true triglyceride triglycerol. So if I look at the structure, here's a glycerol molecule. It's a short carbon hydrogen chain, and they've got 3 hydroxyl molecules on them. So that's where that OL ending comes from, right? And at each of those hydroxyl groups, we'll pull off a hydrogen, and the fatty acid chains also have a carboxyl group on them, from which we'll take an OH group. And those molecules then come off as water. I get free bonds here to connect that oxygen to the carbon. And so that's where we add a fatty acid chain to it. Now I can do that 3 times because there's 3 hydroxyls, and hence the tri in triglycerol. So 3 hydroxyl groups, we take the hydrogens off, and now I can do 3 dehydration synthesis reactions, remove 3 waters, and add 3 fatty acid chains to that glycerol molecule to make what we know as a triglycerol or triglyceride fat molecule. So your major function for your fats are long-term energy storage. This is where your body will take things that you eat either in the forms of fats and store them directly, or we can also back convert things like your glycogen, if you're storing it for too long, back into these kinds of molecules as well. We also use them for cushioning and for insulation, so having 0% body fat is not necessarily a good thing. Your body does need some fat on it for that cushioning of your organs, the insulation of your body, keep your body warm. So it definitely does play a vital role in living things. Animals happen to store it in adipose cells or fat cells. Interesting thing about those adipose cells, though, and this is where things like obesity do become a problem, is that when you build those adipose cells, you never actually get rid of them. You can shrink them, so sort of remove that excess fat storage, but once those cells are built, they're always there. So that does present some issues when we talk about sort of that obesity piece to just human health in general. So you build those cells, it's really easy to fill them up, but you can't ever really get rid of them either, and so it makes it easier to fill them again in the future. While we're on the topic of fats, we can also talk about the difference between saturated and unsaturated fats, and this is going to come down to the structure of those fatty acid molecules specifically. When we talk about saturated fats, these guys are solid at room temperature, and the reason that is because when we look at that fatty acid chain, all you have are carbon-to-carbon single bonds, so it contains the maximum number of hydrogens, or it's saturated with hydrogens. That's where that term comes from. And as a result of them being saturated, they end up forming these straight chains, and so it's really easy to tightly pack those straight chains in molecules. And so they are able to hold their structure even at room temperature. So most animal fats that we think of, butter, fat off of a strip of bacon or steak, right? This is all saturated fat. It's room temperature solid fat. And this is also the one that is most associated with cardiovascular disease, because not only will it stay solid at room temperature, but that also means it's a lot more stable in your body as well. And so it tends to clog up arteries and just be kind of gunky, as opposed to unsaturated fats, which are a bit more healthy in taking in, because they are liquid at room temperature, so they're going to flow much easier in your body as well. And the reason we get unsaturated fats are because they have these double bonds somewhere in their chain. So between two carbons, I've got a double bond. I'm unsaturated. I have less than the maximum number of hydrogens because I've got to remove hydrogens in order to build that double bond, right? Carbon can only make 4 bonds, so if I'm going to make 2 bonds between a carbon molecule, that means hydrogens have to go in order to make that room for that bond to form. But in building that double bond, it actually changes the orientation of the bonds, and it changes the angle at which those bonds form, and so you get kinks wherever those double bonds occur, and that kinking now prevents that ability to tightly pack. And so that's where that unsaturated fat comes from, and the reason it's liquid at room temperature. So most plant oils, fish fats or fish oils, these are going to be your unsaturated fats, and they are considerably healthier from a dietary standpoint. And depending on how many double bonds you have, we can talk about them being monounsaturated, mono being a single double bond, or polyunsaturated, where you've got multiple double bonds going on. We can force it to go the other way. Hydrogenation is a process of converting an unsaturated fat to a saturated one, where we force it to actually add back those hydrogens. So it's naturally a unsaturated fat, and now we force the hydrogens back, we force the chains to go straight, and we force it to be solid at room temperature. So this is where we get things like trans fats from. So trans fats are even worse, part of because of the process that it takes to get that hydrogen back on to straighten that chain back out. So when you look at things like vegetable shortening and things like that, those are a result of these hydrogenation processes. Phospholipids are also a category of lipid, and these guys are incredibly important because they are the major component of your cell membrane. So these guys look a little bit different from your triglycerides. The glycerol is still here in the middle, right? We still have 2 fatty acid tails that come off of those. Those fatty acid tails can be saturated or unsaturated depending on the structure. Typical diagrams will show 1 saturated, 1 unsaturated. And then off that other terminal carbon comes a phosphate group and some choline. So we talk about it having a phosphate head coming off that 3rd carbon, and then the fatty acid tails coming off the other. So those fatty acid tails continue to remain hydrophobic, but that phosphate group is got some charges on those oxygens, and so as a result, that phosphate end ends up being hydrophilic. And that really then aligns to why our phospholipid membrane looks the way it does. So when we talk about forming these membranes in a watery environment like your body, the exterior outside of that cell will be in a very water-rich environment, and the internals, the cytoplasm or cytosol, is also mainly water. And so these phospholipids spontaneously show up in these bilayers because those hydrophilic heads will interact with the water outside the cell, interact with that water in the cytoplasm, and that then ends up shielding those hydrophobic tails in the center from that water. And what that ends up doing is arranging itself in this situation that's going to be able to regulate what sort of molecules get in and out of that membrane based on the chemistry of the molecules we're moving. So when we get to cell transport a little later this year, the idea of the way that this amphiphilic molecule, amphiphilic meaning it's got both properties of hydrophilic and hydrophobic in one molecule, this phospholipid's an amphiphilic molecule, and the fact that it arranges itself in this double layer in the cell membrane really is the reason it can allow certain things in while also maintaining its ability to keep an internal environment that's different from the outside, because it can keep things out as well. Steroids also fall into the category of lipids. When we look at these in terms of their structure, they look considerably different from those phospholipids and triglycerides because they are carbon skeletons containing 4 fused rings. So they'll look like this. So you'll typically have 3 that are 6-membered rings and then a 5th-membered ring here, and then these groups that are coming off of those chains will vary from one type of steroid to the next. A lot of them have this basic component of cholesterol as its starting point. And cholesterol we typically think of as something bad, right? We talk about cholesterol in heart disease and cardiovascular issues. And yet there is a distinct difference. There's your high cholesterol levels versus your I should say your good cholesterol levels versus your bad cholesterol levels, and it's a ratio that your body needs to maintain in order to stay healthy. So having too much cholesterol, particularly the bad cholesterol in your body, is a problem. But you do need some cholesterol in your body, particularly the good forms of it, because it is an essential component of animal cell membranes. When we get to talking about your cell membrane structure in a little more detail when we get to cells later this year, we'll talk about cholesterol sort of working as a temperature buffer. It's going to keep your cell membranes from sort of oozing all over the place if you get too warm. But it also works in the opposite direction as well, that it doesn't get too rigid when you get cold either. So it allows us to maintain a proper fluidity in that membrane as your temperatures adjust because of your external environment. It is also a major precursor for a lot of other biologically important steroids, things like testosterone, estrogen being 2 examples. So some of your major hormones also are built off of the cholesterol structure as well.